Okay, molar mass. To a high extent, probably the calculation of molar mass of a gas using the ideal gas law is going to be the most important portion of these derivations. And I'll tell you in a second why. But this is pretty much the idea. If you recall from the flowchart I presented to you during the stoichiometry lesson, um, we can find the molar mass by using moles or even grams themselves. But more importantly, with the molar mass, we can undergo these changes, right? Now, the reason I'm showing you this particular setup is because of the following notion. Let me show you an example so that this becomes super clear. If we start with, let's say, with the mass of C3H6Br2, we can use the molar mass of C3H6Br2. Now we have grams on top, we place grams on the bottom, the 1 mole goes on the opposite end of the fraction. The grams cancel out and you end up finding out the number of moles. Alright, but this is what I want you to notice. The initial number is nothing more than the mass of the sample. And what we have right here as a conversion factor is the molar mass of the sample. Okay, but the molar mass is in the denominator. So in reality, what we're doing is taking mass and we are dividing it by the molar mass. And what we're obtaining as a result of that division is the number of moles. All right, now the reason I'm kind of showing you this is because we're going to utilize this particular relationship to substitute for the moles in the ideal gas law. Ideally, we're going to have mass divided by molar weight equaling the moles. So that's what's going to happen right here. N is now mass over molar weight. Okay? And what I'm going to do is concentrate on the molar weight first. And what I want to do is isolate it. So if we look at the equation here, what we need to do is multiply both sides by molecular weight, and then we need to divide both sides by pressure times volume. So what's going to happen is that you'll end up with molecular weight on the left side. PV is now in the denominator of the right side of the equation. And what we have here is mass times gas constant times temperature divided by pressure and volume. But another way to reinterpret this is to say that you have mass divided by volume. And you may recall that as being nothing more than the density of a gas. So the molar weight of a gas is given by the density times the gas constant times temperature divided by pressure. But you could also look at it this way. If you don't know the density of the gas, as long as you have the mass and the volume, you can calculate density and input this equation. So we're going to utilize this, once again, based on the ideal gas law, to determine the molar weight of a gas. Alright, so the reason why I am saying that this type of derivation may be the most important one is because when you know the molar mass, you have a means of identifying your gas itself, because the molar mass of a gas is attributed to what kind of elements and what amount of those elements are present within the gas itself. So in this example, I'm saying that you have a collection of, well, you have a possibility of gases. You have an unknown gas that could be carbon dioxide, sulfur dioxide, ammonia, hydrogen chloride, or ethylene. And we don't know which one of these gases we actually are dealing with. But what we do know is that for the particular gas in question, we have a known density of 1.650 grams per liter. And this density is experimentally determined at a pressure of 875 millimeters of mercury and a temperature of 310 Kelvin. We want to know the identity of the gas sample. So when dealing with this type of problem, where you're trying to find out which gas you're dealing with, you ought to think automatically of the molar mass. They're not exactly like, boom, dead on. If this is the molar mass, this has to be the gas. But if you know roughly what the gases could be, knowing the molar mass is definitely the best way to identify the gas. So we're going to first find out what the molar weight of this gas is based on the pressure, the temperature, and the density. The density is in units of grams per liter, and that's perfect because we need liters for the units of volume and we need grams for the units of mass. However, the pressure needs to be in atmosphere, so that will have to change. The temperatures in Kelvin, so that's looking good. So we take care of the pressure, 875 millimeters of mercury. In order to convert this to the proper units, which are atmospheres, we're going to divide the 875 by 760 millimeters of mercury, which equate to 1 atmosphere. So the millimeters of mercury cancel out, and when you carry out the calculation, you find out that this is 1.15 atmospheres. And you can kind of judge whether this makes sense or not. The initial value of the pressure is higher than 760, so this should better be higher than 1 atmosphere itself, which it is. Alright, now we plug in everything into the equation. 1.650 grams per liter times 0.08206 atmosphere liter mole Kelvin for the gas constant, 310 Kelvin for the temperature, and 1.15 atmospheres for the pressure. Alright, so atmospheres will cancel out, the liters cancel out, Kelvin cancel out, and all you're left with is grams divided by moles. In other words, units of molar weight. So the calculation leads to a value of 36.5 grams per mole. Alright, so we got the molar weight. Now what needs to happen is that we need to look at all the possibilities of the gases that we could possibly have. CO2, SO2, NH3, HCl, C2H4. You have to actually manually calculate the molar weights of each one of those gases. And if you do that, you'll find out that CO2 is 44, SO2 is 64, 17 for NH3, 36.5 for HCl, and 28.1 for C2H4. Here is not even a question. You know right away the gas has to be hydrogen chloride because the molar weights match up exactly. And in the laboratory, like if you guys were to do a problem like this, due to errors, because you're not familiar with equipment, maybe you made some mistakes, these values may be a little bit different, and that could create a little bit of confusion. But at least on paper, you ought to be sure that you're going to have values that will be very close to the expected values that correlate to the gaseous substance. Now, the other thing to be said is that not only for the molecular weight, but molar volume, the density of a gas, and the concentration of a gas can only be applied for a substance that you know to be a gas. In other words, don't ever apply the ideal gas law to something that is a solid or a liquid. If you do that, automatically you get marked down. And needless to say, your answer is going to be shenanigans. But ideal gas laws and any gas law should only be reserved for gases and gases only. All right, now let's finish this up by talking about density, the density of a gas. It's a similar point of view as what we have talked about right here, except that we're going to have the opposite end, right? So density is mass over volume, so we need to move volume to the right side of the equation, and everything else needs to move to the left side. That means that we will have pressure times molecular weight divided by RT equaling mass over volume, which is the same thing as density. All right, so as long as you're dealing with a gas, this is how you can find the density of an ideal gas. All right, and to give you an idea, for the gaseous substances, the densities in grams per cubic centimeter or grams per ml are very low. 10 to the negative 5, 10 to the negative 3, 10 to the negative 4, whereas the densities of all other substances, liquids and solids alike, are basically between 1 and 20 grams per ml or grams per cubic centimeter, meaning that the gases are taking up a lot more volume than either the solids or the liquids. All right, so what we're going to do is determine the density of ozone. In this problem, you may think that here we have no information whatsoever, but it turns out to be the case that we have all the information we need. We are being told that this is at STP, meaning that the temperature is 273 Kelvin and the pressure is 1 atmosphere. And we're being told the identity of the gas. Ozone is O3, so we can find out the molar weight by simply taking the atomic mass of oxygen, multiplying it by 3, and voila, you got your molar weight. So pressure, 1 atmosphere. Temperature, 273 Kelvin, based on STP conditions. Molar weight of the gas is going to be 3 times that of oxygen, so 47.97 grams per mole. And now we input everything in the equation. 1 atmosphere times 47.97 grams per mole divided by the gas constant divided by the temperature in Kelvin. the atmospheres cancel out, the moles cancel out, the Kelvin cancel out, and all you have left over is grams per liter. In other words, the units of density. In this case, we found out that oxygen has a density of ozone has a density of 2.14 grams per liter. And the last thing I would like to point out is that based on the formula, not only do pressure and temperature affect the density of the substance, but as long as you have the same pressure and the same temperature, so if you're holding gases in the same room and you're not heating them up, all that will make the difference for the density is the molar weight of the gas. The higher the molar weight of the gas is, the higher the density. And ultimately, this is one of the ways by which chemists were able to tell back in the 1600s whether they had oxygen or they had chlorine or they had some other substance, in addition to performing some chemical tests. All right, so with this, we are done with the derivations of the ideal gas law, and we are ready to get onto the kinetic theory of gases, which will be the topic of the next video.